channel. Today I am going to show you a machine learning model that predicts whether water is safe to drink or not using real data. So I will walk you through every steps from data cleaning and visualizing to data training and evaluating. So let's begin. First, we have imported the libraries like pandas, numpy, Seaborn and all. The second step here will be loading the dataset. We have loaded the water probability dataset. This dataset consists several chemical and physical parameters of water like pH, hardness, solid, chromine, sulfate and more. The target column is called probability, where 1 means the water is drinkable and 0 means it is not. The third step here is initializing the data. Once the data is loaded, we always start the exploration using the head, info, and value count. Just wait, I just count. Value counts. We can quickly check column types. Fourth step here is cleaning our non-numeric data. Real world data can be messy, so columns here contain strange entries. So we create our custom Python functions to detect non-numeric values and clean them using regular expressions. That's why we manually fix a incorrect entry, so our column are ready for numeric conversion. This one. The next step would be converting and fixing the data type. We use a helper function to remove unwanted symbols like percentage sign and kudos, and safety converts that string numbers into real floats. This step enables every column is numeric. Before we start our analysis, you can see all our data have been converted into float. Then comes handling the missing values, that are null values here. We check how many are missing in each columns and fill them with the mean of the existing data. Here, the missing pH or sulfate values are replaced with the column average. This prevents data loss and keeps the data consistent. Now let's explore our dataset visually. Histogram shows how each feature is distributed. Then using a heat map, we check how strongly different parameters correlation with each other and with probability. Here's the data for each one. Let me minimize the screen so that you can get a clearer understanding. This one. It is for pH, hardness, solid, chromine, sulfate, conductivity, organic carbon, and trihalomethanes, turbidity, potability. The next step would be fixing the skewness. This is histogram, heat map. As you can see, we have even fixed the skewness because some features are heavily skewed. We fix this by applying the square root transformation, which helps the model learn patterns more effectively. We have done the skewness for fixing skewness for the chromine and solids, organic carbon as well. See, this is after skew. This was before. The next step is splitting the data. We have imported a twin test split here. To split the data into training and test set, 80% of the data is for training and 20% is for testing. Here the stratify parameters ensure both set maintains the same ratio of safe and unsafe water samples. Then comes the modeling. Model building, like for the task, we use the Logistic Regression Model, perfect for binary classification. Because the data set is slightly imbalanced, we assign more weight to class 1 potable water so that model pays extra attention to identify safe samples. These are the F1 scores in the prediction bar. We evaluate the performance using the F1 score, which balances prescription and recalls, and a confusion matrix to see exactly how a model classifies each cases. A good F1 score means the model is both accurate and reliable. One more thing, in the modeling part, we use the fit function. Since our dataset is slightly imbalanced, we assign a higher weight to class 1, meaning the model will pay more attention to detecting the potable water. Hence, we train it using the fit function and then generates the predictions. So here are the predictions. By default, logistic regression uses a 0.5 cutoff for classification, but in this case, we have lowered it to 0.3 to make the model more sensitive. So it catches more true positives. In real life, it is better to flag potentially safe water than to miss one that actually is. And that I have already said that F1 scored to balance the prescription and recall, a confusion matrix to visualize the result. A good F1 score means the model is correctly identifying safe and unsafe water with balanced accuracy. This is the logistic regression that we have got, and the prediction the threshold 0.3. I have even made a decision tree here. F1 scores are given, prediction threshold tests are done. Here we get the mean train scores and the mean test scores. That's all. This is my complete ML pipeline for messy water data to a functional predictive and model turning. This process shows how data preprocessing, visualizing, and model turning comes true in real-world projects. That's all. If you have found this helpful, don't forget to like the video, subscribe the channel and comment below. And what project would you like to see next? Thank you for watching.